and to tell strings from almost that.
All right. Thanks, Yifan, for asking me to give this talk here. Right, I'm going to tell you mostly about this paper that came out a few weeks ago. I've been thinking about bootstrapping string theory for some time now. And in this latest paper, we actually are able to uniquely land on string theory from literally almost nothing. And I'll make that clear what I mean. But very, very few assumptions lead inexorably to the dynamics of string theory. And we're going to see this in several different guises throughout the talk. It's really a very strong argument. We get both the dynamics of open and closed strings at 4-point and even at 5-point. So evidence is accumulating that string theory really is likely to be the only game in town, which is exciting. And I've been writing these papers with a fantastic group of collaborators, notably Cliff Chung at Caltech, and this latest paper with two wonderful students, Francesco Ciotti at Barcelona and Michele Tarquini at Caltech. So just to put this talk in context, I'm actually not a string theorist, I'm a quantum field theorist. So this talk will occupy one corner of my personal parameter space, but I'm going to be approaching this as a particle theorist, not as a string theorist, because we're trying to derive string theory from the bottom up, not take it as some article of faith from the top down. So just a few words about the bootstrap method in general, which lots of us have probably heard about and even worked on in this room. But in the bootstrap method for discovering or understanding physics, one doesn't impose some high-minded principles of geometry or thought experiments or whatever, or assume a Lagrangian. Instead, you just ask math questions about the S matrix and demanding certain basic minimal properties of scattering along with various physical consistency conditions like Lorentz invariance and unitarity, you land on various theories we know and love. For example, by asking about the unique interacting theory of a massless spin 2 at lowest order in derivatives, one gets GR automatically without having to hurl anyone through elevators, in elevators through space or anything like that. Similarly, you can get Yang-Mills as the unique interacting theory of massless spin 1 at lowest order in derivatives. Now, all of these bootstrap ideas come with some kind of minimality condition. Notice I keep saying at lowest order in derivatives because, of course, GR is not the only Lagrangian of an interacting spin 2. You can add higher derivative terms, etc. And that notion of minimality will play a role in this talk. But what hasn't been really addressed is what is the analog for string theory? What is some very minimal set of mathematical criteria we can impose on the S matrix from which we get string amplitudes automatically. And in the past couple of years, I've been moving toward that answer through this series of papers, and we now think we have a really good answer for that. This is all going to be tree level, yes. All at tree level. First 2/3 of the talk will be at 4-point. The last third will be at 5-point, but if you can derive the tree level string amplitudes for arbitrary massive states on the outside, of course, then you could, at weak coupling, build loop level string amplitudes. Right now, we're just constructing the tree level amplitudes for massless states on the outside, but indeed, going to excited states would be great as well.
Just as a more vague question, I thought the bootstrap, like historically, was supposed to be a non-perturbative statement somehow.
Right. So there are many different bootstraps, right? There's like the conformal bootstrap where you're trying to calculate things involving conformal field theories that may be strongly coupled and that you can't actually get at through perturbative means. But there are also various amplitudes bootstraps going back to Weinberg and before, trying to understand physics we already know and that we can compute at tree level, but understand why it might be unique. So that
to be like the unique perturbative.
I want it to be the unique perturbative answer to some math question about the S matrix. Yeah.
But it doesn't tell us anything about non.
It doesn't tell you anything about non-perturbative. I mean, that's definitely a future directions thing. I think though, getting loop level string amplitudes might be possible from some kind of bootstrap idea, just because, again, from factorization, loop level string amplitudes can be mapped to just the tree level massive string amplitudes. And I think that's obtainable. One reason I think that is because the tree level massive string amplitudes have very little independent structure in the sense that they're almost all kind of uniquely specified by the massless amplitudes. One of the things that Nima Arkarni Hamed and Carolina Figueiredo and I showed in a December paper is that all the massive string amplitude residues are just the massless ones that shifted kinematics, which is totally weird and surprising and not really understood why. We can just show that that's true, but because of that, that's why I think the massive ones will come eventually. Good, great questions. Important to note, as I said, this is not a string talk. This is going to be all from an amplitudes perspective. Right, okay. So what do string amplitudes do? Yes. Oh, gosh. Oh, yeah. That's annoying. There we go. Thanks. All right, so what do string amplitudes do? Well, as advertised, they unify GR and QFT by taming all the Transplanckian issues and graviton amplitudes. But mechanically, how they do this, even at tree level, is you add an infinite tower of massive higher spin states. And massive higher spin states should make you worry, even here at NYU, at the sort of center of the universe for massive gravity, because massive higher spin states generically make your life worse because of momentum dependence in propagator numerators. Adding one or a few massive higher spin states cause tree level amplitudes to blow up more quickly as you go to the UV. So you would imagine needing an infinite tower of massive higher spin states. And that's exactly what string amplitudes mechanically do. Veneziano guessed this answer back in 1968. He was very young when he did this, but he guessed essentially an amplitude without having any notion of what the theory is, that is UV soft. It dies away quickly at high energies, and yet it contains in it a ton of massive higher spin states. So we're asking in this talk, how unique is this answer? We're going to try and get this as an output, and we're also going to get the Virasoro-Shapiro amplitude, describing gravitons as an output, and then ultimately the 5-point open string amplitude. Okay.
Somehow you're going to impose certain asymptotes in those steps.
I'm going to impose certain kind of maximalist UV softness conditions on the amplitude, and we'll find that this is the only thing that comes up. Yep. This has been attempted before. It was attempted most notably in 2016 by Simone Karen-Hill, Zohar Komorgadsky, and friends. This proof is now understood to be wrong. In fact, it was shown to be wrong by Sasha Zhaboidov, one of the original authors of that paper. They claimed that the open string was asymptotically unique, and then Sasha's more recent work showed that a technical assumption they made in that paper about the statistical distribution of zeros of the amplitude is just false. He exhibited various examples that violate that assumption. So it's an open question, hence our interest in this. All right, so a couple of mathematical objects that I'm sure everyone here knows, but just to remind you, that play a major role. The gamma function will be everywhere. It's just the analytic continuation of the factorial. And the important part to remember about the gamma function is that if you give its argument a negative integer, it has a pole. So Veneziano's amplitude has poles at S and T equal to the integers, the famous linear spectrum of the string. The other thing that we'll see over and over again throughout this talk, so in a sense, this is a trigger warning for generalized hypergeometric functions, are these PFQ objects that are just sums of ratios of gamma functions, the so-called Pochhammer symbols. So they're not as bad as they look, but they'll appear in various places. Okay, so the other thing I want to remind you about before we get into the actual argument is what Massimo and I were talking about before the talk started, dual resonance. So this will play kind of a leading role throughout the talk. So in a quantum field theory, we add different channels, different topologies to build an amplitude. That's not true in string theory, where we have just a single world sheet, and the magic of string theory is that you can kind of stretch the world sheet to look like an S channel or look like a T channel, and so you can write Veneziano's amplitude as a sum over S channel poles alone with some T dependent residues, and then magically rearrange it into a sum over T channel poles alone. This is intimately tied to the UV behavior of the amplitude just by straightforward math. So if you have an amplitude that vanishes in the so-called Reggie limit. So if you take S large, the center of mass energy large at fixed T, at fixed momentum transfer, then if that residue at infinity vanishes, you can just show by like 2 lines of complex analysis that you have dual resonance, because you can write the amplitude as a dispersion relation over itself, and you can deform the contour from around the origin or from around S equals S prime to just picking up the imaginary parts on the poles, which are the residues. So it's literally the same thing. So anytime you see dual resonance, just think it means the UV is ultra soft. All right, these residues are also going to play a central role. We're going to try and figure out what the residues are before we figure out what the amplitudes are. And what the residues describe is the spin structure and coupling structure of the states being exchanged on that pole. So the degree of a given residue polynomial tells you the maximal spin being exchanged on that pole.
And just to make clear to everybody, the tree-level assumption is that you only have poles.
Yes, yes. Every function you see in this talk, well, almost every function, will be meromorphic, meaning it's analytic everywhere except at some discrete set of poles in the S or T or eventually U plane. Good. And so you can see immediately that dual resonance and this nice soft behavior means that you have an infinite number of poles. And so you're beyond quantum field theory. You have an infinite number of states just in order to produce the Taylor expansion of the propagator. Okay, good. So that's all kind of background. Now let's actually get into how we're going to try and prove this. So we have 2 sequences that we want to fix. Mu of n, which is the set of masses squared. Here, n is some level. And j of n, the maximal spin at level n. So I can, since n is just some arbitrary label, I can rearrange that label however I want to make the function mu of n strictly monotonic. And then the third function we're going to be interested in is the so-called Reggie trajectory. So what the Reggie trajectory describes is very general. It just means if I take the amplitude and send S large while holding T fixed, the amplitude goes like S to some power, which is a function of T. That power we call alpha of T, and it's the Reggie trajectory.
Say strictly monotonic. I mean, you're also including the degeneracy in this level.
No, because I don't have to do that, because let's say I had 2 levels where mu n1 and mu n2 are the same. Since all I'm interested in is what is the residue at that level, that there's only 1 pole there, so I can break the degeneracy. Yep. Good. Okay. So in string theory, alpha of T is just T, which means that as you go to larger and larger negative T, so larger and larger exchange momentum, the amplitude falls off as the faster and faster power law of center of mass energy. So that's the enhanced soft behavior that string theory enjoys. Quantum field theories don't do that. There's a speed limit to how soft a quantum field theory can be in the UV, so they kind of bottom out. So what we're first going to be interested in are the zeros of the residues, and we're going to show that there are a bunch of zeros that occur in the residues of any Lorentz invariant, crossing symmetric, tree level, and unitary quantum field theory whenever alpha of T crosses certain negative integers. So this will be a prediction from the math that we can then test, not just on string theory, but on various deformations that we and others have written down, which will just be true no matter what. So the general plan here is we're going to first derive these Reggie zeros. And then if we assume furthermore that the Reggie zeros that are required by self-consistency are the only zeros of the residues, that's the minimality condition, we'll land on uniqueness of the string residues. And from there, we'll use an idea called level truncation, this will all be clear later, to uniquely fix the overall coupling of each residue, which will give us the amplitude uniquely. We'll get Veneziano in that way. We'll run through a similar argument to get Virasoro-Shapiro, and then we're going to get the 5-point open string amplitude, which will involve the introduction of a lot more math, but it's basically the same idea. So that's the overall plan. Any questions?
Yeah, I guess at this point, what's the motivation for assuming that you only have certain?
Right, good. So it's in a sense asking what's the minimal theory that's self-consistent. It's almost an aesthetic criterion. We kind of think of it as analogous to asking, like in GR, what's the theory at lowest order of derivatives that is consistent with massless spin 2? It's not the same thing as that. But you certainly could dress all of your residues with extra zeros and get deformations of the string. As long as the sort of fraction of the zeros that are extra in that way is small, even if it's small in a way that's constant as you go up in n, we can generalize our arguments to get uniqueness asymptotically of the Veneziano amplitude. If, however, the percentage of zeros is that are extra is either order 1 or grows in n, then our arguments don't apply.
But you don't have a physics.
No, we don't have a physics criteria.
Expansion is not the same thing.
No, right. I mean, we don't have a physics reason for that. It's just in a sense asking what's the simplest theory I can write down that's consistent with this Regge criterion. Yeah. All right, so here are the two explicit assumptions that we make. So ultra softness, we're going to require that alpha of t is both increasing and bijective for t negative. So it's going to go off monotonically to minus infinity as t gets larger and larger negatively. And so this is not exhibited by quantum field theory, as I mentioned, but is exhibited by string theory. And then the second criterion is the one Matt and I were just talking about, minimal zeros. So every zero of a residue is going to be required to be one of the Regge zeros that will show are required for consistency.
So you are not asking anything about softness of fixed angle.
No, I mean, well, no, but requiring that alpha of t goes to minus infinity as t goes to minus infinity is very closely connected to fixed angle, to the exponential softness at fixed angle, right? Because cosine theta goes like t over s. Yeah.
Could just one very basic question. Could you clarify what you mean by softness?
Oh, yeah. Okay. So here we're interested in the scaling of the amplitude as s gets large. Now, most amplitudes that you would find in quantum field theory would either be constant or blow up when s gets large, right? There's the Froissart bound that tells you what's a speed limit on how quickly they can grow. But really, really special amplitudes like string theory actually get more and more well-behaved in the UV. And we call the behavior of the amplitude going to 0 as s gets large UV softness. It's just the amplitude is getting really, really small. So the theory is getting, in a sense, weakly coupled in the UV.
Okay. So because I always think like when someone says soft, that it's more on shell.
Right. So people, it's confusing because people use soft in different ways in the amplitudes community. Sometimes we talk about soft theorems, which is how an amplitude scales when one of the on-shell external particles momenta is taken to be small. But here we're using softness in the sense of just asking what is the scaling of the amplitude in some limit, and we're wanting the amplitude itself to get small in some limit.
Could one imagine that the real world doesn't have to be ultrasound somehow?
Sure. Yeah. Right. I mean, certainly we can't claim that every amplitude is a string amplitude, right? Like quantum field theory exists. So one has to adopt some extra criterion.
You put down this motivation super polynomial boundedness. Could you say a couple of words on that?
Yeah. So our version of ultra softness is closely related to what's been called super polynomial boundedness in the literature, which is the precise statement is that for every integer k, there exists an open range of t such that the amplitude goes like at most 1 over s to the k at large S. So you can see that more or less requires alpha of t to get more and more negative.
So why would this be a motivation? Like, is there a physical reason that you want?
No, I mean the motivation is entirely, well, almost sociological in the sense that people have looked at various deformations of the string. The best ones, the best behaved ones in the UV exhibit this criterion. But like I said, it's in a sense a maximalist version of good UV behavior, right? That alpha of t goes to minus infinity at t goes to minus infinity. Right, okay. So those are the things we have to buy into. It would be, of course, lovely to show that these criteria are required for any theory of quantum gravity. We kind of sort of think they might be, but this is where we're going, what we're going to assume and see what we can get from it. Okay, first the Reggie zeros. I promised you that I'm going to show you that any self-consistent amplitude has this behavior where if alpha of t goes through certain negative integers, it implies zeros of the residues. This is not unique to the string. This is literally any theory. It's just that in quantum field theory, you can't use this to say very much because alpha of t doesn't go through too many integers, negative integers in quantum field theory because the amplitudes aren't all that soft in the UV. So, okay. So here's our definitions of the residues and the Reggie trajectory again. We're going to take identical color-ordered scalars on the outside. So these are planar amplitudes for now. And first, we can write down a very nice mass-spin relation that relates all three of our unknown functions. This just follows mechanically from the definitions, which is that A of st goes like t to the alpha of s at large t, right? So if you zoom in near a pole, right, at s equals mu of n, the amplitude itself goes like its residue, right? And so t to the alpha of mu of n is telling you about what is the maximal spin on that residue, which will go like t to the j of n. So it follows automatically from the definitions that alpha of mu of n equals j of n for all the integers. So that we'll call the mass spin relation, and we'll use it over and over. So now here's the central idea, what we call the big arc integral in a fantastic naming choice. So we're going to just compute a big contour integral around a circle of radius s star in the s-plane of the amplitude. So this is like an unsubtracted dispersion relation. And we can compute it two different ways. One is just from the definition of the Reggie limit, we know what the amplitude looks like, and so we can just compute it straightforwardly. Now, to be slightly technical, this function here has actually a branch cut along the positive s-axis, so we define this contour to exclude the positive s-axis. Of course, the amplitude itself is entirely meromorphic. This is a function of writing down this approximation, so you don't actually have to worry about that slight gap in the contour. Now, the thing to note is that despite appearances, at integer values of alpha, this integral is actually independent of the radius s star. And you can find this just by straightforward computation. If alpha is -1, the integral is 1. If alpha is some integer not equal to -1, the integral is 0. But then by the fact that this is a meromorphic amplitude, we can shrink that contour to just pick out the poles in the S-channel plane. And so what we get is this big arc integral is just given by a sum over the residues. Now, since this is independent of S star, or equivalently N star, the maximal level, when alpha is an integer, we can differentiate by N star, or we can compute a finite difference. But here we're going to be in the Reggie limit where t is much less than mu of n. So we can send the sum to an integral and compute the derivative. So we get that the residue itself goes like sine pi alpha of t in the Reggie limit. So this factor tells us that there are zeros. There are zeros whenever alpha is an integer. Except, remember, there is this prefactor f of t. That prefactor is there to tell you about the poles in the amplitude when t hits a t-channel pole. So we can't allow t to be on a pole. So there, we should exclude alpha of t where t equals mu of n prime for any level n prime. Furthermore, we've neglected unitarity so far, so now let's impose unitarity, which means we can write the residue as positive sum over Gegenbauer polynomials, Legendre polynomials in 4 dimensions, as a function of the scattering rate. These wave function, these partial wave coefficients are all non-negative because they're the squares of a coupling, right, between the 2 external states and some intermediate state. And just the properties of Gegenbauer polynomials are such that the Gegenbauers are strictly positive when their argument is bigger than 1. And so at large n, where mu and j are both guaranteed to be non-negative, we have the residue is always strictly bigger than 0 for t positive. So we can't have any Reggie zeros at t positive either. So, okay, the summary is that in the Reggie limit, we have these Reggie zeros whenever alpha of t hits an integer, as long as the real roots are such that t is negative and not on a resonance. Now, another nice thing about this is that the Reggie zeros will nest. If some value of t is a Reggie zero of some residue, it will continue being a Reggie zero for all of the higher level residues, just because the Reggie limit gets better and better. So we can check this in some nice examples before running with it, just as a sanity check of our math. So of course it works for the string, right? The string residues are famously these beautiful polynomials, and we find that there are Reggie zeros as expected at the negative integers. What about deformations? So David Gross wrote down an infinite family of deformations of the string back in 1969, where you jam in some exponential functions into the worldsheet integrals. So if we take the simplest possible version of this theory, just for tractability, where we jam in just a constant here times u1 minus u, we find we can actually resum it and write his amplitude in closed form. It's just a string amplitude times the 2f2 function. Okay. We can then compute what the residues are, and we can look for various values of this deformation parameter g, where are the zeros. And indeed, we find that our predictions are borne out. We get kind of chaos at low n, and then as the Reggie limit gets better and better, suddenly it snaps to looking stringy. Same thing happens over and over. For some of these 3-parameter string deformations of Haring and Zhiboydev, we can again compute what the residue polynomials look like. We predicted an infinite number of Reggie zeros because these amplitudes are ultra soft. And indeed, we get the same thing, chaos, and then it snaps to looking stringy when the Reggie limit holds. But this even applies to very, very non-stringy amplitudes. So these so-called bespoke amplitudes that Cliff and I wrote down a couple of years ago, where you take the Veneziano amplitude and you jam into it roots of polynomials. So despite appearances, this thing is meromorphic because we're summing over all the different branches. It has a weird spectrum. It has a quadratic spectrum. It has totally strange Reggie behavior. But we can run this through our algorithm and predict where should the zeros of the polynomials be asymptotically. And they're exactly where we predict from this dispersive analysis. All right, so this works. So now let's use this to land on uniqueness of strings by invoking our assumptions. All right, so far we've just used assumption 1 to find that there's this infinite collection of Reggie zeros, this ultra softness assumption. If we now use minimality, let's say that the only zeros are the Reggie zeros, we can build the residues explicitly. So we're going to start from our result from the big arc integral that the residue goes like mu to the alpha times sine pi alpha. And we're going to take its log derivative in n. So on the left-hand side, we just have alpha up to trivial shifts and rescalings that we don't care about. And on the right-hand side, we have the log derivative of the residue, which in the Reggie limit, you can approximate as a finite difference. It's the log of the ratio of these two residues. And remember what I told you that the Reggie zero condition nests, right? So if there's some residue, some Reggie zero of some residue at some level, it continues being a Reggie zero at higher levels. So if we have the minimality condition where the only zeros are the Reggie zeros, this ratio of polynomials is itself a polynomial that we'll call P. And we can define its large n limit. So P depends on n and t, so we'll take large n limit, and we'll ask about what it can look like. So there are two possibilities. It's either constant in t, or it isn't constant in t.
Is it obviously if it exists? N,
Let's see.
P for an n at large n becomes non-polynomial.
In order for that to be the case, there would have, let's see. I think you could show that there would be some issue with the dual resonance sum converging, right? Because that would mean that the overall coupling of the residue at large n would be somehow growing really, really fast. I would need to think a little bit about that more, but I think you can show that that can't occur if the sum converges. All right, so let's take the non-constant case first. So then P is just T to the K for some power K. And we have a logarithmic Reggie trajectory. Alpha looks like K log T. This is a thing. It's known as the Kuhn amplitude. It's a Q-deformed version of the string. We'll come back to it at the end if there's time. But the Kuhn amplitude literally has logarithmic Reggie trajectories and exponential spectra. But we get to throw it out by invoking our assumption of ultrasoftness, because the Kuhn amplitude actually has a really, really weird Reggie behavior in that.
So is it clear what kind of theory would lead to such an?
Good.
This is not a clear theory.
So no one really knows, in that no one's written down an explicit physical model that lands precisely on the Kuhn amplitude. However, Juan Maldacena and I wrote a paper a couple of years ago showing various non-perturbative string constructions that kind of sort of look like the Kuhn amplitude, in that they have the Q-deformed spectrum, they have accumulation points, they have sort of the weird double log behavior in the UV limit, but they're not exactly Kuhn amplitude. It's an open question. It would be nice to write down something. I mean, one intuition you might have is that there's a notion of Q-deformed integration called Jackson integration, which replaces Riemann integration with some discrete sum. So it would be nice to think that maybe the Kuhn amplitude is telling you about some discretized version of the world sheet, but that's words that no one's made precise. You know, the reason I'm going to throw this out for now and come back to it at the end if there's time is because this isn't ultra soft. As t goes to minus infinity, the Reggie trajectory of the Kuhn amplitude dives off to minus infinity at finite momentum transfer and then comes back up. So we're going to throw it out just by assumption because it violates our ultra softness criteria. Again, if there's time at the end, which there probably won't be, I can tell you about Q deformations some more. All right, the other option is that P is constant, in which case the T dependence is subleading in N. We have P of T is constant plus T over N plus subleading corrections. But it's still polynomial because, as we've shown, P of N comma T is polynomial for all N by minimality. So alpha of T, which is log of P of N comma T, so it's log of constant plus T over N, which at large N still looks like a polynomial in T by the expansion of the log. So what we get is that alpha is asymptotically polynomial. All right. So the residues then, again, invoking minimality, are products of the form alpha of T plus R for R an integer. And since we have bijectivity, R is bounded from below by minus alpha of 0, and we can shift alpha just by multiplying the overall amplitude by some kinematic factor, such that the minimal value of R is just 1. So our assumptions lead automatically to a residue of this form, where we just have some normalization, C of N, that we haven't fixed, some maximum spin, capital N, and some multiplicity factor. Here I'm being very general and not assuming that all the zeros are simple zeros. They might have some multiplicity. So we can compare our residue ansatz that we've, again, derived, not just written down, to that of the string. And we see that our residue ansatz goes like big N to the H times alpha D at large N, just from how we know the string amplitude behaves. But we can compare this to our expression from the big arc integral. And we can use, well, just by staring at it, we see that mu of N goes like J of N to the H. But our mass spin relation told us that alpha of mu equals J. So we get that alpha goes like T to the 1 over H. But we've already proven that alpha is asymptotically polynomial. So H equals 1 is the only option here. Spoiler, that will not be the case for gravity. So we've arrived at the fundamental result that J goes like mu and alpha goes like T. And we can further fix J as a function of N. If I compute a new big arc integral where I do some negative number of subtractions, so I dress my amplitude with powers of S here, and I choose T sufficiently negative that this big arc integral at infinity still vanishes, which happens in some certain range. I can deform the contour again to encircle poles. And now I have some mu weighted sum of my unknown residues at this value of T star. So now I can just count I have J of n star, number of equations I'm required to solve. But the number of variables I have to play with are these r's that appear in the sum, and there are only n star of them. So to have a solution, we need that J is less than n asymptotically, but J is strictly monotonic, remember, and it's integer valued, so it grows by 1 with every level. So it has to be actually bigger than or equal to n. So the only possibility is that J goes like n. And we've derived, again, just from our minimal assumptions, the famous Chu-Frauchi plot of string theory, which came originally from trying to understand nuclear physics back in the 60s, which it's the original raison d'etre of string theory. So that's cool. But we haven't yet derived the Veneziano amplitude, right? Because we still have this unknown sequence, C of n. So this is almost the string amplitude, but I've reweighted all the residues by some unknown coupling. So let's see if we can fix that. Well, what we haven't used, Massimo, did you have a question?
Yeah, so maybe I should have asked it from the beginning. Where do you impose that this amplitude is the amplitude for the tachyon? Where does it come from?
Good.
Not the dilaton.
So, right. So strictly speaking, what I'm deriving is the amplitude of what's called the Z theory in the literature, which is either the bosonic string amplitude, but where every Mandelstam is affinely transformed so that the external states are massless. Or if you like, it's the superstring amplitude, but with all the polarization data that factorizes off out front stripped off. So either way, I've inserted by fiat that my external states are massless colored scalars. That's the mandated assumption. Yeah. And I should say, incidentally, this Z theory amplitude has been studied a lot in the amplitudes community. It appears to be a healthy theory in its own right, at least perturbatively. Of course, we know it can't be a non-perturbatively healthy theory. It's not actually string theory, but it's an affinely transformed version of the string.
So, but is this amplitude the affine transform of, say, the Veneziano amplitude, or is it the amplitude of, say, the dilaton in the string theory?
Well, it's not the amplitude of the dilaton, right? Because these are colored scalars. So eventually, when I talk about Virasoro-Shapiro, you could think of that as some dilatonic amplitude, right? Because when I derive Virasoro-Shapiro, that will be the amplitude for some uncolored, totally Bose-symmetric set of scalars. But here it's some fake massless colored scalars.
Shapiro is for tachyons in closed string.
It's for tachyons in closed string, or sorry. But in a sense, you can think of, I've taken the string amplitude and I've shifted S and T by 1 everywhere so that my external states are massless. Yeah. I could have run through the whole argument with assuming tachyons from the get-go. It's nicer not to. All the formulas look simpler that way. And actually, generally speaking, for whatever reason, in the amplitudes community, when we study the string, we normally actually do this Z theory construction where everything's massless on the outside. But what I was going to say next is that what we haven't actually used is crossing symmetry at all so far, and we should do that. And we'll find that actually allows us to uniquely fix these C of n's. So imposing crossing on this function here is a problem in 2 complex variables. We don't want to do multivariable complex analysis as yet in this talk. So let's turn this actually into an algebra problem using what's called level truncation. So at special values of t, this amplitude becomes a rational function of s. The sum becomes finite. You can see why, right? If I pick t equals a negative integer, this product truncates the sum. So we're going to follow this paper I wrote a couple years ago then to show that this will allow us to uniquely fix the C's. All right, so we impose crossing. We fix s and t both to negative integers. So we have this algebraic constraint on the C's. It's a vastly overdetermined algebraic system. It looks like a miracle that there's any solution at all. And there's only one unique solution you can prove, which is that C of n equals 1 over n factorial. So we find uniquely the Veneziano amplitude, or strictly speaking, the Z theory amplitude, the famous gamma gamma over gamma of open string theory, as the only object consistent with our assumptions.
So
Yeah.
you're showing the Veneziano amplitude is sort of the unique one, but we know for sure that there's some other theory that's not string theory that perturbatively sure will give you something like the Veneziano amplitude, but
That-
non-perturbatively looks different in some way, like
That could be. I mean, this kind of gets at Monica's question earlier. I mean, one way you could try and attack that is, like I said, if we could do this same exercise, but for all massive states on the outside, arbitrary masses, then we would land uniquely on string theory to all orders in the loop expansion perturbatively, which would be more compelling evidence,
it's still not.
but still not non-perturbative. Yeah.
But it's something strange here, because that shift actually.
Yeah.
I mean, people would love to have that shift, and they were never able to get it, right? I mean, there is a famous paper by Lovelace, the 7 reasons why the tachyon is the ion, and they were all wrong. It was a good paper, but so, and that was precisely shifting from -1 to 0.
Yeah.
So what is in
All right.
here that is not in?
All right, but that statement and the spectrum of the string and like the reason the tachyon exists, those are all, in a sense, non-perturbative statements in string theory, right? Whereas here we're interested in just sort of bootstrapping this amplitude, which means there's from the low energy perspective, when you're just asking about the space of functions that do a certain thing, there's not a giant difference between a of s comma t and a of s plus 1 comma t plus 1. Throughout the bootstrap here, we've been modding out by shifts by any affine transformation of the mantle stamps. So in a sense, if you like, you could say that I've uniquely derived the Veneziano amplitude modulo affine transformations of the mantle stamps, and that would be that. I would agree with that.
Then, of course, for this you mean multi-particle amplitudes, and if you have multi-particle amplitudes, then this amplitude satisfy also another condition of this factorization.
Right. So maybe we could uniquely land on it once using 5-point. I'm going to derive the 5-point amplitudes, but again, assuming massless external states. But maybe if we added affine transformations to both 4-point and 5-point, we could fix them.
You need 6
Yeah.
factorization.
Well, right, okay, because it's at 6-point that you're first sensitive to the like the snowflake diagram where you actually care about all 3 massive. Yeah, that's right. Tragically, even for string theory, there is not as yet a closed form expression for the 6-point amplitude. It's a strange situation, 5 or 6 decades in. I want to talk now about non-colored scalars in order to bootstrap gravitational scattering. So again, run through the same problem, but with fully Bose-symmetric massless identical scalars. So I have ST and U symmetry. So I want to parameterize the Reggie limit in a manner that is manifestly SU symmetric. So I'm going to take the S to the alpha and divide up into an S to the alpha over 2 times U to the alpha over 2. That will make our lives easier. And I'm again going to compute some big arc integral, but in an S and U symmetric way. So we get factors of 2 and 1/2 everywhere. And we have poles in both the S channel and the U channel, which are at -S. And so we get some similar sum over residues, but here now weighted by some function of mu and t. So we can do the same exercise, differentiate, and conclude that we have Reggie zeros when alpha of t plus 2r vanishes. So running through our assumption 2 of minimality in the same way, we have some explicit form of our residue. And if I compare these 2 expressions, what I get is that mu goes like j to the h over 2. And from our mass spin relation, we have that alpha goes like t to the 2 over h, meaning h equals 2, because we have already concluded that alpha has to be asymptotically polynomial. So here, Bose symmetry is what mandates that all the zeros are doubled in the gravity case, which indeed is the case for the string. So similarly to the planar case, we can show that J goes like N. So we again have a linear spectrum and a linear Reggie trajectory. And we again have level truncation. So I'm going to just choose some convenient normalization for t and choose the offset for n to be 1, which I can do by multiplying the amplitude by some overall kinematic factor, just to make this look nicer. And I now want to use crossing symmetry to fix the CNs. So we have a dual resonance sum that's manifestly S and U crossing symmetric, but there's still S and T crossing symmetry. So we have the same idea as before, but now we have some different algebraic system for the C of N's that we have to satisfy. So a kind of different algebraic character, but still highly overconstrained with unique solution C of N equals 1 over N factorial squared. So if we plug this in, we get uniquely the beautiful gamma, gamma, gamma over gamma, 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 which is the famous Virasor-Shapiro amplitude of closed string theory. This is literally quantum gravity coming out, because if you ask about tree-level scattering amplitudes in general relativity for massless scalar, or even for gravitons, if you like, if I address this with polarization data, you get some amplitude that blows up at the Planck scale. And then if you ask, what does this look like in string theory, you get some infinite tower of states at the string scale that smoothly that interpolates between a vanishing amplitude in the deep UV and something that looks like GR at low energies. So you got this from incredibly minimal conditions. So that's exciting.
Is this shifted also? The same.
I mean, here, yeah, these are massless. Well, but this isn't shifted, right? I mean, I think the better way to think about it is I've stripped off polarization data. So what I did for the planar case is I derived the open string amplitude, but with the polarization data of the gluons stripped off, the f to the 4th term. Here I've derived the closed string amplitude for gravitons, but with the Riemann to the 4th stripped off. So it's on a similar footing in that way. And that doesn't involve any affine transformation. That just involves saying I'm going to derive some amplitude, but I'm going to multiply it by polarization data eventually. Good. So now, in the last part of this talk, I want to tell you about what happens beyond 4-point. So here, we're actually going to have to do some work on the string side before we can even talk about bootstrapping it. Because the standard Kobe-Nielsen form of the string amplitudes that you can look up in a textbook is kind of bad in that it doesn't converge in the interesting part of kinematic space. Namely, it doesn't converge near the poles. So if the funding agencies were very kind to us and gave us an accelerator of truly enormous proportions, and an experimental particle physicist who wanted a prediction of what happens near, say, 10M string for 2 to n string scattering at tree level, would get no answer from the theory community, unfortunately. We literally cannot evaluate the Kobe-Nielsen amplitude everywhere. Now, if we want to then bootstrap the 5-point string amplitude, we better have an answer for what this looks like at arbitrary kinematics. So we can do that. We're going to use these so-called U variables that Nima has been writing a lot of papers about recently to write the amplitude in more convergent form. And this converges if and only if S51 is negative. So we've improved things. We can go near the poles in 4 of the channels, but not in 1 of them. So at 5-point, there are 5 Mandelstam invariants. And it has known form in terms of a 3f2 hypergeometric function. But that's still not enough. There's still half the kinematic space that we don't know about. Thankfully, the mathematical community has been studying 3f2 functions for around 150 to 200 years now. And there's a giant web of identities that's still being mapped out. A particular use are these so-called Tomé transformations discovered in the 1870s. You can rearrange the parameters of the 3f2 at the penalty of getting ratios of gamma functions. So we can use that to write down a nicer version of the 5-point string amplitude where all of the factorization channels, or all of the poles, are explicit times some different 3f2. But again, this only converges in half the space. And combining these 2 forms and even modding out by overall cyclic invariance, there's still some forbidden sliver of Mandelstam invariance where the amplitude is unknown. Enter Whipple's identity from the 1920s, which trades a 3f2 for a 6f5, which naively looks like a bad trade, but it's better because it's a 6f5 evaluated at -1. And if you remember what the definition of the PFQs look like, this means it's an alternating sum and therefore has better convergence properties. And we can use this to write down a version of the 5-point string amplitude that converges literally everywhere. You can put this on Mathematica hit Shift Enter with numerical kinematics, and it will spit it out for arbitrary kinematics.
So the expression you gave is as a radius of conversion is equal to 1, so it's equal to
Sorry?
the expression you gave in terms of a series has a radius of conversions equal to 1. So it's a little bit tricky.
It is tricky to conclude that. That's because the definition of the hypergeometric, the generalized hypergeometric series are, I mean, it's kind of like the Riemann zeta function, right? You define it in some region, you analytically continue everywhere. Yeah. Thankfully, there are standard analytic continuations that are known for all the PFQs. So here I'll prove this to you just by example. So if I fix 3 of the Mandelstam invariants and plot in the remaining 2, here's the region where the standard form converges. The Tomé transform version does better, but still leaves a hole. And our version, of course, converges everywhere. And in overlapping domains of convergence, they completely agree. So we now know the 5-point amplitude for string theory for the first time. The analogous version of this for 4-point, where you go from the Kolbe-Nielsen integral to the gamma gamma over gamma, was solved by Euler. That's why it's called the Euler beta function. All right, so let's see if we can now, using our newfound knowledge of the 5-point string, actually bootstrap it from first principles. So we first have to ask about what is its Reggie behavior like, because we've gotten all of our mileage out of asking about the Reggie behavior. This is also a thing that was not understood before. What does the n-point string amplitude look like in the Reggie limit? Because there's not just one Reggie limit, there's a whole set of alternative Reggie limits where you take various factorization channels large. So we're going to figure that out. Using the techniques that Emma and Carolina and I introduced in the paper in December, we can find what happens when we take the double Reggie limit of S1 and S2 large. And again, it's morally kind of like S to the T, except now there are 2 different S's and there are 3 different T-like invariants, but there's still S to the T behavior. So we can do a double big arc integral, right? Integrating over both S1 and S2 and see what happens in the Reggie limit. What we get is that some double sum over residues can be expressed in this way, where we get these sign of pi times various t-like invariants. So we can predict where the zeros of these residues are in the same way as before. We differentiate in n1 and n2, and we predict that there are Reggie zeros when a1, a2, and a12 are integers, satisfying some positivity conditions. Now we can compare that against the known closed form 5-point string residue, and we find complete agreement. Good. So now let's actually turn to the bootstrap. So we're going to write down a completely arbitrary ansatz for the residue. We know what the masses are, right? Because we already fixed them at 4-point. They're integers, n1 and n2. We know what the maximum spins are. They're also n1 and n2. And so I can ask, if I exchange particles of mass n1 and n2 of maximum spin n1 and n2 through this channel, what's the completely arbitrary residue polynomial in my 3 t-like invariants that I can write down? And it's this. It depends on these lambda ijk's. If I now demand that this object vanishes on the Reggie zeros predicted by just imposing the same Reggie behavior as the string, we land uniquely on the 5-point string residue. So the 5-point residues of a totally arbitrary planar amplitude are uniquely fixed by demanding the same Reggie behavior as the string. So now we've almost gotten the 5-point string amplitude uniquely up to some sequence here that depends on these 2 level integers. So what remains? Well, crossing, which is cyclic invariance at 5-point. So it turns out there's a notion of level truncation that works at 5-point. So remember, at 4-point, when t was a negative integer, that was nice because the dual resonance sum became a finite sum and crossing became an algebra problem. The same thing happens at 5-point, except now the dual resonance sum is over an infinite plane. And we have 3 t-like invariants that we can fix to integers. And when we do that, that infinite plane collapses to this diamond-shaped region, whose shape we know. That's uniquely fixed by the residue structure. So now we have some algebra problem for the C and 1 and 2s to solve using cyclic invariance. We can do that, and the unique solution is that C equals 1 everywhere. So we get uniquely the 5-point string amplitude, again, from this kind of Reggie zero bootstrap, just demanding them that all the zeros are the zeros imposed by the Reggie scaling. So unless we have time to talk about Q deformations afterwards, that's all I have time for. But what we've done, just to remind you, is we've identified a set of these two simple conditions, ultra softness and minimality, that uniquely land you on the open string amplitude at 4 and 5 point, and the closed string amplitude at 4 point. We don't know about the closed string amplitude at 5 point because the same exercise has not yet been done even to understand the string amplitude there. But there are lots of open questions, many of which we've talked about. Can we do this at 6 point and beyond? What about loops or non-perturbative questions? Those are all great questions that we would like to bootstrap as well. But it's exciting because it's only through investigations of this type that we can really characterize this full space of options for quantum gravity. And this is the first set of conditions you can write down like in 2 sentences that uniquely give you string theory. So I think we're on the right track in that way. And just broadly speaking, there's a lot of exciting work to be done kind of at the intersection of the modern amplitudes program and sort of quantum gravity first ways of thinking. And I think this is kind of where a lot of the future of physics is going to be in there. And there's many different manifestations of this. But I'll take any questions, and then maybe we can talk about Q deformations if there's time. Yeah, Monica, I saw you.
So here, I think it seemed the fact that there were 2 S variables and 3 T variables had to do with the fact that there were only 3-point interactions. So do you know, like, is that also an assumption?
Oh, no, sorry. No, at 5 point, if you just mod out by the on-shell condition that pi squared is 0 and that p1 plus p2 all the way to p5 equals 0, then there are only 5 Mandelstam invariants.
Then when you generalized your analysis, you treated 2 of them as S and 3 of them as T.
Oh, yeah.
It seems to be. It felt like that was actually relied on the fact that there were only sort of 3-point interactions that were built.
Oh, yeah, sorry. I mean, that, well, let me see.
Or there was a gauge in which all your Feynman diagrams were used.
So since we're interested in planar amplitudes, we're guaranteed that all the poles are among the planar Mandelstam invariants, which are the S's and T's that I wrote down. We're also assuming ultra softness, which means in the 5-point context that I can write down the amplitude as a dual resonance sum over completely factorized channels. So that statement that there are in essence only 3-point interactions you can show follows from the 5-point version of ultra softness. And indeed, it's true of the string. Like there are no fundamental contact interactions in string theory, except for 3-point. I think Marius, I think you had a question first.
Yeah, I was just thinking. So these assumptions are quite interesting, right? Like you say, ultra softness doesn't hold for quantum field theory, but I obviously don't pretend that quantum field theory is a good UE theory of our world.
Right.
Like I wonder if you try to assume ultra softness doesn't hold, and you try to think about gravity, whether you could find some kind of weird behaviors or contradictions, or I just wonder whether there's any way of approaching those assumptions and say, let's see what happens if we don't
Right.
keep to them. So
I mean, indeed, the Kuhn amplitude fails ultra softness, right? But it's still dual resonance, just not at t equals minus infinity at finite t. So there might be reasons to relax that. Yeah. Massimo, either way.
I'm going back again to the intercept. In string theory, it was a very positive outcome of the fact that you have a tactic. Right?
Yeah.
The intercept of the Reggie projector is -1.
Right.
Then you could derive that there is a massless vector or a massless gravity.
Yeah.
So with all the spin structure, etc. Here, you have thrown away that.
Right, because we've said, well, I'm defining everything only up to affine transforms. Yeah, indeed. Yeah. That's true. I mean, one could add that as an additional assumption that I'm going to assume some Reggie intercept. We were trying not to do that. We were trying just to talk about the asymptotic behavior of the.
And maybe related to this, you are looking at very special, so far, very special outside states, but
Yeah.
so can you see the difference between, say, string, superstring, type two, type 2A, type 2B, because that depends on the Ramon sector, right? If you just
Yeah.
put the bosons.
Yeah.
Those unless you put Ramon states on the outside, you never
Right.
see them.
I mean, it would be a more complicated analysis. It'd be something that in principle we could do just by essentially running through the entire analysis again, but addressing the external states with say polarization data or Ramon charges or whatever. Yeah, it's not something we've done as yet.
So I'd like to ask the following question. Imagine that I have in quantum field.
Yeah.
And we know that we can use effectively as coming from the state. Forget now about it.
Mhm.
Now, can you use, suppose that you start bottom up completely. You start with a quantum field theory, and then using, when we try to have an effective field theory, then we have some problems.
Yeah.
Now, using arguments like not the ones, simple arguments, can somehow discover the state, you know what I mean? Because,
Yeah.
you know, we're doing the opposite, right? Swampland is the opposite way.
Right.
I mean, we have, every quantum field cannot be coming from the string, and then we're using, but now using this method to go.
I understand the question. So you're asking if I don't impose even like ultra softness or any UV assumptions, if I just look at effective field theory alone and ask, can I somehow use constraints on effective field theory to resum to get to the string? So people have looked at that. People have tried that. There are kind of mixed results in that. So one thing that you might hope for is that so there is this so-called EFT hedron, right? There's some space of boundaries for where EFT coefficients can live. If string theory lived like right on a corner, right, of the EFT hedron, if it was in danger of violating unitarity from many different directions, and it was very unique, then yeah, you could imagine bootstrapping the string purely from EFT coefficients. And people have found that, well, okay, in some of the EFT coefficients of the string live fairly near the boundary. Rostelli has a nice paper on this, but the fact remains that most EFT coefficients of string theory live in the bulk of the EFT hedron and not at any incredibly nice location. So it seems hard without invoking additional assumptions. So Henrietta Elvang from Michigan has tried invoking additional assumptions and tried to do a numerical bootstrap of from the EFT to get string theory in that way. But those additional assumptions tend to be very strong, like invoking string monodromy or invoking supersymmetry or something like that. That constrains your EFT coefficients, and you can get uniqueness sort of in that way. But it's just relying on unitarity of the EFT alone. It seems that you can't bootstrap string.
I'm asking this because before you were born, in the first days of the 80s, beginning of the 70s, there was a theorem by Conwell, Topos, and Lawrence Smith,
Okay.
that they were putting the opposite. They were saying that the maximum field I can get for the normalized theory, it is Young-Mills field theory with spin one and with Patana breakdown. And then they start from the unitarity and somehow they get to gauge theory. That was somehow almost like what you try to do here.
But that was based on assumption of a finite number of parts. So and indeed, I mean,
No,
here it's essential to have a Regge trajectory and the Regge behavior. That's the thing that they couldn't have.
Right. But yeah, I mean, we get the prediction of an infinite number of particles like immediately from the assumption of ultra softness, just I mean, like in the first few slides by dual resonance. But yeah, I mean, the general question you're asking is a good one. Like if I, have even fewer UV assumptions and just ask about unitarity of EFTs, can we get uniquely string theory? And it seems like no, there has to be more than that assumed.
But if you impose ultra softness directly at level of EFT,
I don't know what that would mean, right? Because ultra softness is a statement fundamentally about what the amplitude looks like in the UV, whereas the EFE is by construction blind to that.
But people try to impose various UV difference.
Oh, sure. I mean, I've written things about this. I had a paper a few months ago, actually, where we showed for the first time how to impose unitarity on amplitudes beyond 4-point, right? Where you don't have an optical theorem. One way to impose unitarity is kind of building amplitudes like Tinker Toys, right? Write down all possible 3-point interactions and stick them together. That's difficult. A nicer thing you can do is this Hankel matrixology, moment curves, etc. that we found. And actually, you can use that to constrain deformations of string theory, like David Gross's deformations. So maybe unitarity at all multiplicities plus additional assumptions about ultra softness might land you uniquely on string theory in a way that's of a different character than what I described here, but the jury's out on that. All right, yeah.
Can you consider external massive string states also with this like shiftiness in here, or is that something that?
It's more complicated. It might be possible because so I alluded to this funny fact that Nima and I found in December at the beginning of the talk, which is that so take an n-point string amplitude and ask about its residues where you set maybe one of the internal propagators to some massive state, or 2 of them, or 3 of them, or however many. What you get is a lower point massless string amplitude, but at affinely shifted kinematics, where the point s's and t's have all been shifted by integers. It's totally weird and surprising that this is true. It follows just from the explicit form of the string amplitude. I mean, certainly if you adopted that as a bootstrap condition, you could get a lot of mileage, but why that should be a bootstrap condition, I don't know. Yeah. All right.
So, thank you
Thanks.
again.